We continue the review of advanced engineering mathematics, and we're here in chapter 4. In chapter 2, this book is cover the number of methods for obtaining analytical closed form solution of first order differential equation. And chapter 3, the book covered the equation of second and higher order and found them solution and the different methods and the basic concepts. In chapter 4, the book cover discussion of linear equation, but in here, the solution of the non-constant coefficient equation. This case in respect constant coefficients homogeneous, constant coefficient non-homogeneous, non-constant coefficient equations is third case in the solution of the higher order differential equation is much more difficult than the non-constant coefficients case that we do two things, much more difficult than the constant coefficient case. In here, the book considered only second order equation and give up the prospect of finding solution in the closed form and seek the solution from the infinite series. So in here, the book in chapter 4 basically gives some introduction, the series, then it's give the overview of the review of the power series and infinite series and some of the summation, infinite sum concept and partial sum, and in here use some basic theorems and Cauchy convergence theorem of the series. Then now in here focus on the specific needs for this chapter power series and define the power series and so on, and give the theorem interval conversion of the power series and some examples. Another theorem is the manipulation of the power series, so on. If we continue, if we want to go more deep knowledge and deep understanding, you need to go and read these chapters, and it's defined the Taylor series form in here like this. We call this the Taylor series. Just continue. In the section 422 power series solution of differential equations, the theorem is for power series solution is give the any linear homogeneous equations give the power solutions, power series solution like this in here. So on. I just continue when I see some important highlights and the concept. I just start and mention that. Otherwise, of course, every knowledge in this book is important to understand the mathematical concepts and the physical meanings of the many things to analyze them. And just continue. Again, it's so closure. You see, it gives summarize what's happened, what's told in this chapter, and computer software. You can use the Maple to solve some series problems in here, and exercises give. And after that, if we continue to go to section 4.3, section 4.3 is give the method of Frobenius method. So it's given like a singular points and ordinary points definitions. Let's give the definition here. Then this section is give you the as a section 4.3.2 the method of Frobenius of the solution of the differential equations. In here you see the solution example here. So just continue. And if we go to section 4.4, in here Legendre function and definition of Legendre polynomials and equations and solutions. In here power series, and if we go another section in here, section is 4.5 is singular integrals we call the gamma function in the solution of the differential equations. Let's give you some overview of the gamma function of solution, how to utilize the gamma function and the differential equation solutions. So in here it gives some basic concept and theorems and all the necessary things to understand this section. If you go to section 4.6, in here we see the Bessel function and differential equation and how to solve the concept of the Bessel function. And later in the course of the transfer phenomena, the solution of some differential equations, we see all these concepts in, and the book of the transfer phenomena gonna mention all this concept, and later you can come back and you can read from here to get the detailed knowledge to understand the solution of the differential equations. In here I'm just gonna show all these things available in this book and different chapters. So if you go continue like here, okay, some review what we saw in this chapter. So the power series, the series solution of the differential equation, exponential integral, gamma function, Legendre equation, Bessel equation, and midfield Bessel equation, and equation reducible equation of Bessel equation, and so on. So we come here to chapter 5. Chapter 5 is introduced to the Laplace transform and introduced the definition of the Laplace transform and the equation of the Laplace transform. And basically in the inside of the chapter it gives some basic understanding and properties of the transform, Laplace transform. Let's give topic by topic. Then we continue like this, and in the 5.5 give some application, the solution of differential equation of the Laplace equations, give you singular system of the differential equation, how can they solve by using the Laplace transform in this chapter. Let's give some discontinuous forcing functions, and we call it step function. Define the step functions. 5.5 section. And section 5.6 is give the forcing function of impulse function as important topic. You can review from in here. Then additional properties of the related Laplace transform, 5.7. You can see here, so review and Laplace transform derivative and theorems and transformation, application, the solution of the differential equations. So we come here, the chapter 6, the quantitative methods of numerical solution of differential equations. As we saw in the undergrad course, numerical related to course of numerical methods, they gave some basic insight how can the numerical methods can be used in the solution of the differential equations. It gives some introduction. 6.2 Euler's methods to solution of differential equations. You are familiar this concept from the undergrad courses. And 6.3 give some midpoint rule and Range-Kata methods in here. And 6.4 is give application of the system and boundary value problems. How can we apply this quantitative methods to differential equation solution? And the topic of the stability of different equations covered in here. There are very important concepts inside of this section. You can go and read and review here. And chapter 7 is qualitative methods. In here, phase plane and nonlinear differential equations, different than the chapter 6. As defined, what's the phase plane? And 7.3 singular point and stability, existence and uniqueness, two important concepts again here. So we now hear the topics of actually we call here after that point, after that chapter, we call here the part of the linear algebra. We know this from the undergrad system of linear algebraic equation. We can solve them. Let's say you have system, you can derive, let's say you are calculating some mass different let's say you have different kind of species ABC. Let's say you derive some mass balance equation to represent the ABC, the elements of in your system. Let's say you have three different algebraic equation. You want to find, you have three unknown and you need to have three equations. So you can solve this equation simultaneously by using the linear algebraic equation, let's say Gauss elimination method introduction. You know this from the undergrad. So basically after this part, chapter 8, it gives you some linear algebra chapters. When we go over with the chapter 8, for example, in chapter section 8.3, it gives you solution by Gauss elimination methods. You can find all these things in linear algebra books and courses, and Gauss elimination steps and concept, definition of the concepts. And another topic, Gauss-Jordan reduction, pivoting the concepts, and so on. So in its review of the chapter 8, it gives you some solution method of the system of algebraic equation. So vector space, this is the important topic. It's covered the very basic knowledge we need to know to understand the physics in transport phenomena and to analyze them. So you know what is the vector from the high school? So geometrical representation of any vector and properties of the vector, summation of vector, multiplication, scalar multiplication, so on. It gives you some basic introduction in section 9.1 and 1.2. It's give you in the section 9.3 introduction to angle and the dot product. Basically between two vector, let's say u and in here u and v, you have two vectors. There is an angle between two vectors, and we can define the dot product u point v, basically multiply. We call this representation, this mathematical operation is the dot product between two vectors u and v. The dot product between u and v is if length of the u, norm of the u, multiply norm of the v and cosine theta of the angle between two vectors. If u and v is different than 0, if u and v is 0, then it's give you 0 result. Basically, what is the physical meaning of this dot product? You see, you take the projection of the u on the v like this. The projection of the u on the v's give you length of norm of the u multiplied by cosine, and in here like this. Then if you multiply this the norm of the v, it gives you the dot product here actually. By way of the geometrical interpretation, observe figure 2a in here that norm u and cosine theta is the length of the orthogonal projection of the u on the line of the action of the v, so that the u dot product of u and v is represented norm length of u and v and cosine, and it's give this length of the v times length of the orthogonal projection of u on the line of the action of the v in this direction. So this is the definition of the dot product. For example, if you go over this example, work done by the force in mechanics, the work represented by the W done when a body undergoes a linear displacement from the initial point A to final point. Let's say you have some body initially at the point of A, some force kind of acting on this body and is taking this body to from initial point A to final point B. Under the action of the constant force acting on this body F, is represented in the figure 3, is defined as the length of the orthogonal projection of the F on the line of the displacements. You see the force acting on the body, the projection of this force acting on the body is represented by this arrow in assisting on, because this F is assisting the force, it's taking the body from the point of the A to the point of the B. So based on this definition, based on the displacement of, we mean the length of the vector of the AB. What does this represent? Displacement, how far B from the AB with the head of the B and tail of the A. But that product is that product of the F with the AB. So the work done on this body to take this body from the point of A to the point of the B gives the dot product between the F, the force acting on body, and AB, the vector of the AB, you see from here actually. So this is the good example of to understand the physical meaning of the dot product. So this give you the U is equal to U dot product U is in square is give you the norm of the length of the any vector itself. So this is the definition of the dot product. Another concept in section 9.4. So we can the representation of the vectors in two space and three space by introducing the alternative representation of the in terms of the two tuples and three tuples. We can represent a vector in any space. For example, if you go here, if I want to represent any vector in the two space, you see I have just two elements on this space by donated in here are R square, and I have the two elements A1 and A2. Briefly, in three space, I represent R here like this. Then I have three elements A1, A2, and A3 in here. In the back page, give some properties of the vectors in summation, multiplication, so on, scalar multiplication. Another section is give you dot product, norm, and angle for n space. Give some dot product between u and v is represented like here, and we can represent here. Norm of any vector is can be represented here. Angle between the two vectors can be represented by this formula in here. And another section, subsection 9.5.2 gives properties of the dot product is important. As it give you the properties of the norm in here. You see, it's give you the definition of the orthogonality, and two vector is orthogonal each other if dot product of these vectors give you 0. So orthogonal set is, let's say you have the set u1 and uk. If all the dot product of this vector each other is give you 0, then you have some orthogonal sets. Let's give some example here. In normalization, we can normalize any vector by this. We call this a vector of unit length is called unit vector. So orthonormal mean a set of vectors is said to be orthonormal if it is orthogonal, and if each vector is normalized. Let's say you have some set of vectors. If they are orthonormal if they are orthogonal each other, and if this set is orthogonal and each vector is normalized. It's called the Kronecker delta here. We are gonna talk about this more detail later about this concept. Now I skip briefly. So I continue. So in section give some 9.6 generalize vector space. What is vector space and properties of vector space, like here. Inner product and norm here. So requirement of inner product, let's say here, requirement of the norm here is give the dot product between two vector again, norm of the any vector. Let's say norm of the between two functions is given like this. So closure in here. Then it give another linear algebra concept, span and subspace, definition of span and subspace, and some definition theorems, You can find all this knowledge in the undergrad course, and you can find also in this book. Cover everything. So definition of the section 9.8 linear dependence is give this linear dependence here. I just want to continue, and section 9.9 basis and expansion and dimension here. So section 9.10 give best approximation, and what is the theory beyond this best approximation, and you can find here the definition and derivation of the best approximation is give this result. So review, you see we see dot product and angle between two vectors, the properties dot product and norm, what is the best approximation, so on. So chapter 10 is give another important topics you know from the undergrad, and matrices and linear equations, the algebra, matrices and matrix algebra. We can represent any matrix in this form, and row and the column. You can call all this line is the column, and you can call this line is the row, the vector. So is now matrix addition. How can add two matrices each other? Is another theorem. Matrix multiplications. And when we continue, there are many other detailed concepts. You need to go read them. I think you are already familiar with all this concept from the undergrad. Okay, in here, the another concept of transpose of matrix. You know, if you take the row of the matrix, make it a column. If you take the matrix column, make it a row, you take the transpose of any matrix. You see here, you take the row, make it column, and row is column, row is column. We call this transpose of any matrix. This matrix, not any matrix. Okay. Again, it's still cover every determinants of the matrix. There are another important topics cover here in this book. Now is there the another section of the rank application to the linear dependence and the existing uniqueness for the form of Ax equal to C. Solution of this. Section 10.6 is giving insight of the inverse matrix, the Cramer's rules and factorization, so on. In here you see LU factorization to solution of the linear systems, algebraic system or differential equation systems. The section the 10.7 give the change of base is optional, but you can still go read and to understand the concept. Okay. Another section is 10.8 is give it vector transformation is optional. But transformation is very important for our class of the transfer phenomena to understand the basic concept. So review of the chapter 10. So chapter 11 is give you the concept of the eigenvalue problem. What is the eigenvalue and what is the solutions of eigenvalues? Finding the solution. You can find here, chapter 11. So chapter 12 is the extension of complex case is optional. I just skip this chapter through the chapter 13. So differential calculus of the function of several variables. You say you have more than one variables, and differential calculus of this function has more than one variables. We call all these things is available in chapter uh, 13. Chapter 13 is important. It gives you some basic concept. What are functions and what is the definition of mapping and or transformation? Let's say you have some x value, the function of f's, taking this value, the fx, we call this mapping or transformations. Then the section 13.3 is give you partial derivatives. If the x derivative of this function exists at the x0, it's called a partial derivative of f with respect to the x at x0 and y0. You see, we can represent any partial derivative of fx, partial derivative f respect to x is can represent it like this, or say like this. You see here derivation of the fy in a similar case. And this is the second order partial derivatives. Partial derivative x, partial derivative f respect to f. So we can be represented like this, or fxx, or fxy, or xyx, or fyy, like this. You can go here, higher order representation of the partial derivatives. You can find here. And section 13.4 is composite function and chain differentiation. We call here this is the chain rule, and the theorem is chain rule is given in this equations. You can find here to apply the partial derivative. So section 13.5 is get Taylor's formula and the mean value problem. We call here, we can represent the Taylor's formula. Here is this is the reminder, like this. So implicit function and Jacobians. Implicit function and Jacobians. Another important topics. We are gonna see this concept in transfer phenomena and understand the basic concepts. So let's give you implicit function theorem and Jacobians. You see here the the theorem is show implicit function theorem and multivariable case and definition of the and section 13.6.3 define the Jacobians and the formulation of an examples. You can go and read. Now section is 13.6.4 is give application to change of variables. You see these examples, good example, temperature variation inside of your system respect the direction of the x and y in a second order differential equations here. Then let's give you the section 13.7 and definition of the maxima and minima. And section 13.8 gives Leibniz rule. We are gonna use it in the derivation of the equation and transport phenomena. So basically, all the things I mentioned here, later we will come back, and when we need the more detailed knowledge, we will come back and we will read and we will explain more detailedly. But now I just want to mention here the concept we are going to utilize in the transport phenomena, conservation law derivations, and so on. So this is the actually end of the chapter 13, and chapter 14 is the cover the vector space vectors in the tree space. Actually, in transport phenomena, we're gonna involve the analysis and derivation of the equation in the tree space x, y, z. This either is like Cartesian coordinate or cylindrical coordinates or spherical coordinates, and we are gonna deal with the in tree space. So what is the dot and cross product? The meaning of the dot product we explained before is, you know, the meaning of the dot product. So we define what's the perpendicular and orthogonal sets. We define all this before. And another concept here, the cross product of between u and v, we represent by u cross by v. So what is the cross product between the two vectors? Give this if u and v not 0, and give 0 if u and 0. Actually, what we obtain by using the right hand representation, the cross product between u and v give you this vector here, another vector. The magnitude of this vector is give you the area of this area here. We call this the cross product. So section 14.3 gives you Cartesian coordinates, and here Cartesian coordinates. Cartesian cylindrical and spherical coordinates we consider, but in here starting by Cartesian coordinates by two elements in here, because I and J here, and for the tree space similarly sorry, again if you go back, For the 3 space, we can add I, J, K. Similarly, for this 3 space, suppose that we adapt the Cartesian x, y, z coordinate system with the reference vector I, J, K, like this. And so on. Now, another topic is the section 14.4 is give you multiple products. We defined what is dot product and what is cross product, but we can combine these two things together. For example, let's say if you have the 3 vectors, you can obtain dot product between v and w, and dot product of u also dot product of these 2 vectors. And you can get the dot product between these 2 vectors, and you can get the cross product between you and this dot product result, and so on. We call this triple scalar triple product and vector triple products, or so on. We are going to define these things later. Optional topic is the non-Cartesian coordinates. This topic is define the plane polar coordinates and r theta. Then in later it give you the transformation between Cartesian coordinate and, for example, let's say cylindrical coordinates. Let's say if you want to transform from the Cartesian coordinate to cylindrical coordinate, you can utilize this section. And spherical coordinate, let's say transformation between the Cartesian coordinate x and the spherical coordinates y, z, like here we can use this formulas to transform interchange between 2 coordinates. So chapter 14, in here the dot product and cross product and non-Cartesian coordinates and so on. Now chapter 15 is give you some definition of what is curves and surface and volumes. And actually I'm gonna continue in the other video the chapter 15 and other chapters in this book, and I'm gonna finalize the reviewing of the advanced engineering mathematics in the next video. See you in the next video.